So today's topic is Waec type questions and answers on electronic configuration and the periodic table. So we're going to be flipping through some Waec type questions that you're likely to meet on the topic of electronic configuration and the periodic table. So come along with me and let's do this together. All right. An electronic configuration describes how the electrons in an atom are distributed. Okay? So that is a little background. And know that there are two types or notations. There are two types of electronic configurations or notations. Now, there's a KLMN shells notation, and there is the SPDF notation. The two types of electronic configuration are the KLMN shells notation and the SPDF notation. Okay? Now, the KLMN notation shows only the number of electrons in each of the shells. You see the K shell, L shell, M shell, N shell, so on and so forth. The notation shows only the number of electrons in each of those shells. Okay? While the modern SPDF notation subdivides the shells into subshells or energy levels. See, the second type of electronic configuration we have is the modern SPDF notation. And what it does is that it subdivides the shells into subshells or energy levels. Okay, come along. Now, what you notice that the KLMN notation of the first 20 elements shows that electrons are added to a shell until a stable duplet of 2 electrons is reached in the first shell, or an octet configuration of 8 electrons is reached in the shells that follow. The KLMN notation of the first 20 elements shows that electrons are added to a shell until a stable duplet of 2 electrons is reached in the first shell, or an octet configuration of 8 electrons is reached in the shells that follow. Okay, let's step back a bit to understand that statement. Now you can see hydrogen is 1, K1, helium is 2. Now this is a stable duplet for helium. So helium has a stable duplet because the K shell can only take a maximum of 2. The K shell can only take a maximum of 2. The L shell can take a maximum of 8. The M shell can take a maximum of 18. But for the KLMN shell notation, it usually takes just 8, right? So you see, K has a maximum of 2. It cannot go more than 2. So if you see, look at this last column here, the KLMN shell notation column, you can see K2, L1, K2, L2, K2, L3, K2, L4, so on and so forth. So this is a stable duplet. Helium has a stable duplet, okay? Or an octet configuration. Octet configuration in the shells that follow. Let me repeat this statement. The KLMN notation of the first 20 elements shows that electrons are added to a shell until a stable duplet of 2 electrons is reached in the first shell, like I just showed us, or an octet configuration of 8 electrons is reached in the shells that follow. Okay, so let's quickly get there. An element is put into a period based on the number of shells in its atom. Okay, so we count the number of shells to tell you what period an element belongs to on the periodic table. You count the number of shells to know what period an element belongs to on the periodic table. So just to recap, hydrogen and helium belong to the first period because they have just 1 K shell, right? Then lithium down to neon belong to 2 periods because they occupy both K and L shells, right? Those are K and L, those are 2 shells. So lithium down to neon belong to the second period. Similarly, or moving ahead, sodium, you can see three shells, K2, L8, M1, 3 shells. See 3 digits there. down to argon, 3 digits. So sodium down to argon belong to the 3rd period. Okay, moving ahead, potassium and calcium belong to the 4th period because they occupy 4 shells, K, L, M, and N shells. So that's how periods, that's how elements are grouped into periods. Okay, for the groups, to know the group, you just look at the number of electrons, the outermost electrons. See here, lithium has 1, ends with 1, beryllium ends with 2, boron with 3, carbon with 4, so on and so forth. So lithium belongs to group 1, beryllium to group 2, boron belongs to group 3, carbon to group 4, nitrogen to group 5. Okay, remember? Okay, so let's really, all right, now it's time for your Waec type exercises. It's time for the Waec type exercises. Okay, all right, question 1. If an atom of an element X is represented as, see, element X is represented as mass number of 4 and atomic number of 2. Element X is represented as this, having a mass number of 4 and an atomic number of 2. Okay, you recall that notation. That's how we represent elements, symbols, in short, showing the mass number on top and the atomic number below. In some cases it could be the other way around, but the larger number is usually the mass number. Okay, now the question says, which of the following statements is or are correct? Okay, if an atom of an element X represented as this, which of the following statements is or are correct? Okay, so if you look at the options there, it should tell you that it will help you to identify these elements, to initially identify it. So what elements do you think has mass number of 4 and atomic number of 2? That should be the second element on the periodic chart, which are on the chart we just saw. That's helium. Remember your first 20 elements, helium is the second element. So that's atomic number of 2. So this must be helium. And remember, helium was an example we treated to be chemically inactive. Okay? So X must be chemically inactive. That's an inert gas. Helium, X stands for helium, so it must be chemically inactive. Option A is correct. Option B, let's look at option B. An atom of X has 2 neutrons. Definitely, that's correct. Remember, the number of neutrons is gotten from subtracting the atomic number from the mass number. So 4 minus 2. If you do 4 minus 2, it gives you the number of neutrons. So an atom of X must have 2 neutrons. So option B is also correct. An atom of X has only 1 shell. An atom of X has only 1 shell. If you see the configuration for helium, if you go back, configuration for helium on your chart here, helium is number 2 up here. So you see the configuration has just 1 shell, the K shell. So that means option C must be correct, also has only 1 shell. X belongs to period 1 of the table. Yes, that's only 1 shell, so it must be up to period 1. So C and D are saying the same thing, must belong to period 1 because it occupies only 1 shell. The electrons occupy only 1 shell. E, all of the above, is the correct answer because A to D are correct statements. So the correct answer is option E, all of the above. Okay. So next question, question 2. Which of the following electronic configurations belongs to a noble gas? Which of the following electronic configurations belongs to a noble gas? Okay. So if you look at the SPDF, this is an example on the SPDF. Okay, you want to know how many electrons. You want to know how many electrons. Yes, to help you to know how many electrons are in this element that's being represented here using the SPDF notation. So how do we do that? How do we do that? How do we find the number of electrons that is being shown in this configuration? You simply add up the superscript numbers. You simply add up the superscripts. So see those numbers that are on top there. 2 plus 2 gives you 4. 2 plus 2 gives you 4. So that means this element has 4 electrons. Okay, 4 electrons, you tell you that that should be beryllium. Beryllium is the 4th element. Then option B, 2, 2, 6, 2, 3. Okay, so this is the KLMN should be now 2, 2, right? We convert all of these to KLMN shell notation. To solve this quickly, I advise that you convert it to the KLMN shell notation, right? So this becomes 2, 2, right? Option B says become 2, 8. 2 plus 6 becomes 8, is it not? So 2, 8, 5. 2 plus 3 is 5. So this, the KLMN for this element will be 2, 8, 5. You see? 2, 8, 5. And 285 is not the configuration for a noble gas, right? Noble gas must have a stable duplet or octet, right? A duplet in the first shell and an octet in the following shells. So this is stable duplet here, but this is not an octet. So it has 2, 2. So this option A is not correct. Option B is also not correct because it has 5 valence electrons, right? For a substance to be a noble gas, it must have 8 valence electrons, okay, in the following shell. This is option C is 2, 8, 8. 2 plus 6 is 8. Here, 2 plus 6 is 8. And then 2 plus 6 here is also 8. So this is 2, 8, 8. You see, that's a stable octet. Option C is a stable octet, right? So let's put that in mind. Let's proceed to the other options. This is 2, 6. 2, 6. 2 plus 4 is 6. So this is 2, 6. And this is not a stable octet, right? Then this also option E now is 2, 8, 1. 2, 8, 1. That's not a stable octet or duplet. So the correct answer should be C. Option C is the correct answer. So it's option C is the electronic configuration that belongs to a noble gas. I hope that's clear. Okay.